And yeah, it's an unlimited attempts. Can take the attempt many times until you can correct your mistakes. Okay. And what else? So I will post the problem set, I think, when we finish the third PowerPoint. Okay, so we will continue with our lesson still on ionic reactions. Right. Again, I would like to emphasize, no? So when you study in organic chemistry, you really need to practice writing the reactions and analyzing where the electron goes. So for organic chemistry, we just have to look at the organic reactions without taking down notes and writing the equations. Particularly, you have to write all the bonds. Look, you have to emphasize the electron, the unshared electron pairs, the bonds. You have to find where is the partially positive carbon, where is the nucleophile. Now you really have to think for that. No, otherwise it will be hard to see where would the bond go, or the formation of new bonds would go. Okay, so last meeting we discussed about the SN1 reactions, and we talk about the difference between the SN1 and the SN2 reactions. So today we're gonna discuss what would favor SN1 or what would favor an SN2 reactions. And last time we also learned what is the difference between the substrates used for an SN1 or favored for an SN1 reaction, and the substrates favored for an SN2 reactions. And the SN1 and the SN2 reactions, they would favor different kinds of substrates. So you have to identify if it's a 1 degree, 2 degree, 3 degree alkyl halides. Okay. So for an SN1 reactions, no, according to the Hammond-Laffer postulate, it says that the transition state structure for a step that is uphill in energy should show a strong resemblance to the structure of that step. For example, now, if you remember in the SN1 reaction, the first step would always be the formation of the carbocation. And so the transition state, or the first intermediate product, will be the transition state, or rather the carbocation. And the transition state structure for a step that is uphill in energy should show a strong resemblance. So we will have to look at the diagram later. Okay. So check on the diagram here. 6.10. Okay, so here you will see that transition state, no? Whichever transition state would be close to the product. No, so it says here that should have copied that. there should be a strong resemblance to the structure of the product of that step. So if you notice, the transition state should be close to the product of that particular step. Now, when you see on the energy diagram for the reaction coordinate. I don't know if you understand what I'm talking about. So I'm gonna copy again the energy diagram. This one is the complete, for example, here. Saan ako ang slides? Anyway. Like here, for example, you see in the slides here, your transition state, you have your product. So for this particular step, whichever transition state that is closer, transition state structure that is uphill in energy should show a strong resemblance to the structure of the product for that step. So this is your transition state, for instance, and this is the product side, transition state products, this particular step. Step 1, initial reactant, transition state product. I don't know if you can see my cursor. This becomes your reactants for step 2, transition state and product. For step 3, reactant 1, transition state, and your final product, of course. So whenever, when you are going uphill, the transition state, whenever you have a transition state, whichever transition state that would have a strong resemblance, that would have a similar energy to that of the product, they will have a strong resemblance to its structure. So kung pare-pareha siya o close siya sa yung free energy, then the structure will be similar to the product if the transition state would have a very similar energy to that of the product. So here again, we consider the reaction of our reactant here, tert-butyl chloride, and then there is this leaving group, the blue one, the chlorine, would leave to form the carbocation and the ion chloride. Okay, this is the product. This is for the first step, no? So before your carbocation is being formed, there is what we call as this transition state, and this is the one that you see kaning mga inani, no? And first, step 3. Step 3 na tanan siya diri, but kaning first na curve na itong makita, kaning sa ubos, that is your initial reactant, transition state, product. So I'm saying, okay, so reactant, before it really forms your carbocation, that is your first intermediate. So there is this what we call as a transition state. So in the transition state, it resembles product of step. This is our product, and this transition state will have to resemble that of the product sa kanilang step, no? And so if you look at the transition state, there is this chlorine partially leaving your carbon here, and then so your chlorine will bear partial negative charge, and your carbon will bear partial positive charge. So, and then it will finally leave, and carbon will get the positive center, and chlorine will get the negative charge, positive charge for carbon. So you notice here that the structure of the product, no, is similar to the structure of the transition state. Carbon here bears the positive charge, and in the transition state resembles to that of the product. Carbon will bear partial positive charge. Okay. So since the product of this step actually an intermediate in the overall reaction, this is the product, no? For this step lang, I have to emphasize, but of course we learned that this is only step 1 for the overall reaction. The final product, of course, is different. It will be an OH. But for this particular step, step 1 of the SN1 reaction, you will form a carbocation. And the carbocation that's being formed is an intermediate product. Really gid siya ang final product. So before that intermediate product 1, napatay gitawag nga transition state. Okay? And again, when you look at the reaction coordinates of curve, you have your reactant, transition state, product, intermediate product rather, 1. And this intermediate product 1 become the reactant of the reactants of the next step. So again, this becomes the reactant of the second step, then you form a transition state, and then product of the second step. So the product of the second step will become the reactants of the third step. If you can see my cursor, so reactants of the step 3, your transition state, and your product. So for the last step, should become your final product now for the overall reaction again. I hope that you were able to follow that. Okay, so since the product of this step is a carbocation, any factor that stabilizes the carbocation, such as dispersal of the positive charge. Now, we've already talked about that last time. No, whatever that could disperse the positive charge, katong atong giingon ka last time, no, which includes hyperconjugation, the inductive effect, particularly the electron donating inductive effect, and of course the resonance in which the positive charge is developing. So anything that could stabilize the positive charge would lead to the formation of your product. So a methyl primary and secondary alkyl halide would have to ionize to form methyl primary and secondary carbocation to react by an S1 mechanism. This carbocation, however, are much higher in energy than tertiary carbocation, and the transition states leading to these carbocations are even higher. So we've learned, of course, that the most stable carbocation can be formed with a 3-degree alkyl halide, no? Because the carbocation to be formed is stabilized. So when we are dealing with primary methyl primary secondary alkyl halide, no, the formation of the transition states would require very, very high energy. So when we are dealing with 1 to 2 degree alkyl halide, no, the activation energy actually for the reaction is very large. So if it's very large, the reaction would be so slow. Okay, I don't know if you can see that on the screen, but I actually, so 30 minutes, I actually indicated or made a link, no, for the second meeting, the third. But before I will share the second and the third link, when the meeting ends in 5 to 15 minutes, no, I would like you to click again the link that I sent you if it will be working or not. Okay, and if it won't be working, I will share the second link. So I don't know how Zoom will work. Anyways, let's go back to the discussion again. So here, if you are dealing, for example, okay, here, for example, you have, let's look at first the red, no? So the red, when it forms a transition state, no? Pag it forms a transition state, you notice that from the reactant to the transition state, there is only a very small difference in the free energy. I mean, the free energy of the transition state is very, very small, no? Gamay rang i-climb the reactants to form the transition state and to form your products. If you compare with this blue one, no, from the reactant to the transition state, there is a large energy difference, no, in such a way that to do that, to reach the transition state before the product, it will take such a long time, no, because the energy is very high. It needs a lot of energy to overcome, to form the transition state before it goes to the product. So this is an example of what I've mentioned earlier, depending on the reactants, no, even if it forms the products. For reactants, for example, in an SN1 mechanism, no, if we are dealing with a 3-degree alkyl halides, and stabilization of the transition states to form your product, no, katong sa carbocation, can be easily dispersed, or the build up of the positive charge on this build up anemia. If we're dealing with tertiary or 3-degree alkyl halide, so dali ra ni siya ma-climb, no, because in the formation of this developing partial positive charge here, mas stabilize man siya in alkyl groups, because these alkyl groups could have electron donating inductive effect. So whenever you have an alkyl group close to the or attached to a positive carbon, no, the alkyl groups can help stabilize or disperse the positive charge by inductive effect. Murag i-share niya yung electron density from the alkyl groups para ma-stabilize na siya. And then you will form your product. So this is the case that an example, what you will see, this is the red one. So dali na siya because transition state will be stabilized to form your, of course, intermediate product. If you compare it, if we use a reactants, for example, a 1-degree alkyl halide, no? To form your carbocation here, and before it forms the carbocation, can you product might first form the transition state. And because in the reactant side, itong alkyl halides, there is not so much alkyl groups that could stabilize the developing positive charge. It will take such a long time from the reactant to the transition state to be formed because it will require very high energy. So according to Hammond-Leffler postulate, one way that the postulate can be stated is to state that the structure of the transition state resembles the species that is nearest in its free energy. So there's two types of transition states that would resemble the product side. I mean, there's two types of reactions, when you can have an exergenic step. Exergenic is when you form negative delta G. Okay, so here you have a product for the red one. The delta G is lower than the delta G of the initials. Its delta G is negative. For the blue one, the delta G is positive. We call that intergenic. So according here, that whenever you have here, for example, the blue, the transition state here resembles that of the products because there is not so much difference in their free energy. Here for the red one, the exergenic structure, the transition state resembles the reactants and structures because the transition state would have a close energy to the reactants. So let's have a practice. So last time we talked about solvolysis reaction. Whenever we have solvent that is involved in the reaction, like water or alcohol, methanol, ethanol, and they also become our nucleophile. So in cases like that, we call it a solvolysis kind of reaction. Okay, so here the question, the relative rates of ethanolysis of 4 alkyl halides are as follows. So CH3, CH2Br, that's a 1-degree alkyl halide. The rates of reaction, ethanolysis. So which means if we say ethanolysis, our reactant here is unsa or nucleophile. What does this mean? Okay, let's review. Last time, now we talked about solvolysis reaction. Now, solvolysis again is a reaction, nucleophilic substitution reaction in which the nucleophile is our solvent. So for example, here, our nucleophile is H2O and it will substitute bromine here to form your OH. It's H3OH, H3OH, ethanol. Also the solvent for this reaction, and it will be the one to attack the carbon here. So being a solvent and being the nucleophile, we call the reaction solvolysis. So when we say ethanolysis, ano naman siya diri? Dapat earlier di siya question. So when we say ethanolysis of 4 alkyl halides, what is our nucleophile here?
Ethanol.
Okay, ethanol. Okay. So tapad sa iyang sa H3 alkyl halide, there is this rate of reaction. So the rate of reaction for this ethyl bromide is 1, and this propyl bromide is 0.28, and this 1, 2, 3. Okay, so that's 2-methyl propyl bromide. Okay, the rate of reaction is 0.03, and CH3C, CH2Br is 0.0042. The question is each of these reactions likely to be SN1 or SN2? So isa-isa ho nato no for each of this kani. CH3, CH2Br, kani nga mga substrate. So how do you explain that one? Problem set na lang ako sa inyo. So let's say CH3, CH2Br 1.0. Do you think that, so you notice here that the difference or the difference is on the kind of substrate, right? And we use the same this we use ethanol as our reactant. So I would like you to answer this 6.11 and tell me. So if you remember, there is this difference in the SN1 and SN2 types of substrate, right? And of course, you've learned that for SN1, it favors a tertiary alkyl halides, no? So that you will form a tertiary also carbocation, a 3-degree carbocation. For an SN2, it will always favor a methyl or a 1-degree alkyl halide because there is a concerted attack, no, from the back. So, and you notice for all of this, these are all SN1 kind of reaction. SN1, sorry. These are all alkyl halides that are 1 degree. Tama? So CH3, CH2Br, CH3, CH2Br. Okay, nag-differ lang siya sa alkyl groups na nasa last. But then you notice that even if they are all 1 degree alkyl halides, so there is the difference in the rates of reaction for the reaction with ethanol. So the question is, would each of the reaction be SN1 or SN2? Provide your answer. Okay, so I would like you to think for that and tell me the answer next time. So now we focus on, last time we talked about the effect of the substrate, no? Which one would favor SN1 and SN2 reaction. Now we also consider what would be the effect of concentration and strength of the nucleophile. Of course, you learned that for an SN2 reaction, the SN2 being bimolecular, no two molecules are being considered for the rates of the reaction. The nucleophile and the substrate both affects the concentration of the nucleophile and the substrate, both affects on the rates of reaction. But for SN1 reaction, no, the SN1 reaction, the rate of the reaction is only dependent on the concentration of the substrate, the concentration of your alkyl halides. So in this case, no, it is not affected by the nucleophile. So for example, if your nucleophile is for example, is a hydroxide, no, it's not affected by the strength of the nucleophile, whether it's concentrated or not. So the rate of SN reaction is unaffected by either the concentration or identity of the nucleophile because the nucleophile does not participate in the rate determining step of the SN1 reaction. If you remember, in the SN1 reaction, the first step is the formation of a carbocation. And that formation of carbocation in this first step is a very slow reaction. Since it is a very slow reaction, in a multi-step reaction of SN1 reaction, the first step in the formation of carbocation becomes the rate limiting step. So since it becomes the rate limiting step, it is the step that overall determines the reaction. And in that step, we don't see any nucleophile, okay? And so the overall reaction actually for an SN1 is only dependent on the concentration of the substrate. So regardless of the nucleophile would be high, concentration is high or low, or the identity of the nucleophile, it doesn't matter with SN1 reaction. For SN2, of course, it would matter, it will affect. So a good nucleophile is one, how do we say if the nucleophile would favor SN1 or an SN2? A good nucleophile is one that reacts rapidly in an SN2 reaction. Again, in SN1 reaction, we don't care whatever the identity of the nucleophile, whether it's concentrated, we're using a very high concentration of the nucleophile or a very low concentration. it doesn't matter. It only matters when we are talking of the SN2 reaction. So a good nucleophile is the one that reacts rapidly in an SN2 reaction with a given substrate. A poor nucleophile, however, pag mo react siya rapidly, no? So pag mo react siya rapidly, of course, you can easily see in the rates of reaction that's very, very high, no? The rate of reaction is very high. Pag very slow ang reaction, in an SN2 reaction with the same substrate under comparable reactions, then we have a poor nucleophile. So as mentioned above, we cannot compare nucleophilicity with regard to SN1 reactions because nucleophiles does not participate in the rate determining step of SN1 reaction. So let's compare, for example, the relative strength of the nucleophile. So let's have the substrate here, in this case, H3I. Okay, two reactions here, and H3I. So in the first reaction that you see in the slides, the nucleophile is H3O minus. No, it's negatively charged, running out of time. We have 10 minutes. It's H3O minus, okay? And for the second reaction, we have the same substrate. Our nucleophile is H3OH. No, kanisha is negatively charged. No, probably the source of this can be sodium. Of course, nani siya partner. Pag negative na siya, yung partner metal and tag-positive ion, normally like sodium plus, okay? In water, it always dissociates to form ions, H3O minus. So here, the source is H3O Na plus, of course. Okay, back to the discussion. And the second one, our nucleophile here is H3OH. And for this reaction, it's very slow. So when it reacts, this is an SN2 reaction, no? You have to remember that it is concerted, kind of reaction is concerted, and to produce your product. The product is H3O, CH3, and I. And here you have CH3O, CH3. So the I will leave, okay, and you have O plus here. Of course, this can be removed by using another base, no? To obstruct this hydrogen, to react with positive hydrogen here, and the bond between oxygen and hydrogen will be returned to oxygen so that you don't get a positive oxygen. Okay, so there is a further step in here, but if consider like dali lang tama steps of reaction. No? Of course, I have to say that the positive oxygen here, this is not the final product actually in a real setting. We will have another few steps to remove the hydrogen here para CH3O, CH3 po na makuha. There is another step for that. Anyway, so here in the reaction, the first one is very rapid. The second one is very slow. So you notice that depending on the nucleophile, no, the relative strength of the reaction is different. So the relative strength of the nucleophiles can be correlated with three structural features. Number one, a negatively charged nucleophile is always a more reactive nucleophile than its conjugate acid. Okay, let's have an example for this one. So here, this is a negatively charged nucleophile, and this one is its conjugate, can be its conjugate acid. Okay, so here the negatively charged is always a more reactive nucleophile, and that's why you can see here in this illustration that negatively charged nucleophile here is the reaction. By using this negatively charged nucleophile, the reaction is very rapid as compared to a neutral nucleophile. So for example, if we compare OH and H2O, okay, so OH is the conjugate base of H2O. OR negative is the conjugate base of ROH. Now remember your conjugate acids and bases in your Chem 130, we discussed about that. No, so the negative one is a more reactive nucleophiles compared to the, did I record? Naka-record data?
Yes, ma'am.
Okay, naka-record data. Are you still with me? Hello, everyone. Are you following me?
Yes,
Yes,
ma'am.
ma'am.
Okay. So again, so we're looking at the features of the nucleophile. Now, since again nucleophile is not affecting the SN1, so this only pertains to an SN2 reaction. So the relative strength again of the nucleophile can be affected by the charge of the nucleophile. Number one, okay, the more negatively charged nucleophile, the conjugate base nucleophile is better nucleophile than the conjugate acid of the particular nucleophile. Number two, in a group of nucleophiles in which the nucleophilic atom is the same, nucleophilicities, parallel basicities. So, unsay pasabutan na. So, oxygen compounds, for example, show the order of reactivity. Unsa lang nucleophilicity? Nucleophiles are species that seeks a positive center. So, they also contain electron pairs and sometimes they also have contains or they also bear negative charge. Basicities, pasabutan na basic substances. There's this definition that we learned in the Lewis definition. A base is a substance that donates an electron pair. Remember that? Or a substance that in the Arrhenius definition is a substance that dissociates from the hydroxides. But in the Lewis base definition, the base is a substance that donates its electron pairs to the acid, Lewis acid. So Parihar actually no, by definition or by the thought of it, nucleophiles and base are actually the same. In fact, nucleophiles are bases, but not all bases are nucleophiles. Okay, so nucleophiles, mangita gina siya o positive center. It's always a reagent, it's always a reactant. Namang may base that contains okay, parihar na. So here you have so here in a group of nucleophiles in which the nucleophilic atom is the same. So you notice here that the nucleophilic atom is O, oxygen. So OR, lahi lang ang partner ni oxygen. It's negatively charged. Here it's OH. Yes. RCO2. Unsa ng RCO2? It's C double bond O and then C bond to oxygen. So the oxygen, one of the oxygens contains only one bond. It's the conjugate base of the carboxylic acid, RCOH. And then the ROH and then the water. So our nucleophile here is oxygen, 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 oxygen. So you notice here that these are the bases, no? It 6 also it also can donate electrons to a Lewis acid and nucleophiles also. So this also the order of the basicity. So the OR, OH, OR is more nucleophilic than OH, then RCOO, then ROH, then H2O. Why is that? Okay, so the one that we'll look at the structure. Here you will have an R. An R is an alkyl group. Now, an alkyl group, I have already mentioned earlier, have an electron donating inductive effect. So kung kinsa may silingan niya, it has the tendency to donate electrons sa iyang silingan nga atom. Okay, that's why kung positive ang iyang silingan nga atom like carbon, it can disperse the positive charge. Okay, but si R being an alkyl halide, kung makasilingan siya ng oxygen, so si R can have an electron donating inductive effect. So katong effect akong gi-mention before, inductive effect, no, electron donating inductive effect. I-induce niya mo, induce siya electron density paingon sa iyang silingan nga atoms or group of atoms. Okay, so kung negative na daan si oxygen here, and then it will induce an electron density, saying silingan ng oxygen, then oxygen will bear more positive, more negative charge. Okay? So, i-compare ni mo kang OH here, wala siya R. So, and because of that, OR will be more nucleophilic. And of course, more basic. So, CRO kaysa OR kaysa kang OH. Okay? Compare na to kang RCOO minus. Okay. So, in the RCOO minus, the electrons in oxygen exit. Exit. Stop share na lang. Okay, we will look at the structure of. Okay. So since it's RCOO minus. Okay, so we'll do the structure and we will draw